Thank you so much for the introduction, Abhishek. As he said, I recently graduated with a master's in aerospace engineering from UFM. I specialize in mainly gas dynamics, which is computational fluid dynamics, as well as reduced order modeling and optimization. So I made sure to take some courses on that. One thing that this entire presentation is about is essentially higher order methods, and in particular the discontinuous Galerkin finite element method, and that is something that's really exciting. One second, I will just share my screen now. I hope you can see my screen.
Yes, ma'am.
Yeah. This is essentially discontinuous Galerkin FEM for computational fluid dynamics. Basically, I'm assuming everyone here is from some sort of engineering background. Is there anyone who does not know what CFD is?
I think so. We have few people. I'm not 100% sure they are present in the call, but there were few people who signed up who might be from more of quantum side. But I think so. In general, everybody is from engineering side.
Okay, fine. Anyway, I will just give a brief overview of what CFD is and why we need CFD in the first place. So, computational fluid dynamics is basically essentially the analysis of fluid flow, heat transfer over an object, and to analyze the properties of all of that, and to essentially gauge the object's reactions to physical phenomena and make engineering decisions based on that. So one particular example is sea flow over a car, and if any of you follow Formula One, you would know that a lot of aerodynamic design is based a lot on CFD, and there's some very great designers who have done very impressive work with both wind tunnel as well as simulation insights. Now, CFD alone is cannot be used. You need for some sort of design verification, you would need experimental validation as well, and that but hopefully because of costs, people are slowly and shifting towards the CFD side. Also because the improvement in technology is astounding over the past few years. So anyway, so as you can see, CFD has two different types, which is the physical basis and the visual basis. So the physical basis is what we generally look at, and the visual basis can be particle systems, that is with direct simulation Monte Carlo, like those kinds of methods. They're more statistical based, but they're not very used very often, except for certain very specialized flows, such as rarefied gas flows, which is like in the upper levels of the atmosphere. Physical basis, there are two different types, which is Lagrangian and Eulerian. So Lagrangian essentially means that you follow along with the particles in the flow. You assume that you can see the individual flow particles, and you follow along with them and try to trace it over a certain distance. And you try to to derive the flow path lines, so to speak. It's like being in a river and following along with every single droplet that goes along with it. So that's the more intuitive way of looking at it. But it's also, it's, I would say, not very, it's kind of mathematically complex, which is why we see more of Eulerian techniques, which is, so Eulerian techniques is just, is as you're observing the fluid as a continuum, which is like not discretized into several particles, So essentially, it means that sitting at the bank at a particular point in the bank of a river and just watching it flow and making observations on how the flow looks like at every single point, be it velocity, pressure, etc. What it means is that we view the entire flow as a field and with specific properties, physical properties at every point. So in this Eulerian description, we have so the basic equations of fluid dynamics, which are called the Navier-Stokes equations, which are a set of continuity, momentum, and energy equations, which are, as of now, pretty much impossible to solve unless you make several simplifications. So one particular way of looking at it is RANS, which is Reynolds average Navier-Stokes, which is essentially saying that, okay, I have my velocity, pressure, etc. I will split it into like a mean part and a fluctuating part, which is like you want to account for the uncertainties in the flow as well, which is why you have the fluctuating part. When you have a mean part, you can just say that, okay, I'm on an average, the flow, my fluid essentially moves through these particular locations. You cannot be very specific, but you can say that, okay, on an average, it moves in a particular way. But any fluctuations, which is that any eccentricities in any particular direction, that is what the fluctuations account for. So what Reynolds did, he was a very great fluids engineer, was that he simplified the Navier-Stokes equations by splitting the main velocity field into a mean part and a fluctuating part. And he sort of derived this set of equations where one part could be directly solved, be it numerically, and the other part had to be modeled. So once you simplify a set of equations, there's always, what it means is that you make it look simpler, but there is always a part which trips you up, which is that, it is actually more complex than it is. And that is the turbulence part of it. The main fluctuating part is the turbulence part. And that is what people use several turbulence models to sort of converge. So when they say they want to solve the RANS equations, they would always say that I'm solving the RANS equations a particular way, and what your turbulence model is. Now, the turbulence model is used to converge to essentially model what is called the Reynolds stress term, which is a very key thing in visualizing the turbulence in the flow. Turbulence is basically inherent uncertainty. So so your turbulence, your Reynolds stress, so to speak, that's what it's called, like that particular fluctuating term, the stress due to the fluctuating quantities in the flow, right? In either direction. This can be U, V, or W, that is in the X, Y, or Z direction in the currently the space that we can visualize, which we interpret as three-dimensional. So so that particular term can be modeled, which is that you make certain approximations to say that this is what I think the turbulent term should look like, and I hope that my solution is compatible with this. And based on what you know from the physical nature of the flow, say you're looking at flow through a pipe, it looks like a particular way. You can say which turbulence models are the best for this particular type of a problem. So certain types of turbulence models are K epsilon, K omega, Spalart-Armalas, etc. So K epsilon basically means you're solving the kinetic energy term and kind of like a turbulent dissipation term. K omega is solving for the kinetic energy term and something else. So it's basically different ways of solving a set of equations to sort of converge to the Reynolds stress term, which is the turbulence stress term, and then you can solve the main set of equations. So a very key part of Reynolds average Navier-Stokes is getting the right turbulence model for your particular flow situation. So another way is another different view of Eulerian flow solutions is LES, which is large eddy simulation, which is like saying that, okay, I have a chaotic flow. I'm going to divide it up into large scale and small scale interruptions, right? And I know that I can directly solve my equations for the large scale terms, which is that the big vortices that you see in the flow. But for the small scale terms, I will do something like my turbulence modeling in runs, which is that I will model it. I will say that I think it should look like a particular way. And hopefully, like my physical flow is also compatible with this. The other is that you don't do any modeling at all, which is like ideally what every engineer would love to do, which is DNS, that's direct numerical simulation, which is that you directly solve your Navier-Stokes equations. But the reason this is not done, except when you have a large amount of computational resources, is that it's very time consuming, and it is only possible for very small or highly very simple flows. Like for example, like imagine a flow through a channel in 3D. So that is something that is very simple. That has no free surface effects. Like so, I don't know, like it's not like simulating the ocean. It's a very enclosed chamber, and you know what the material of the pipe is like or your channel is like, and you kind of go from there. So it is very simple. But this cannot be done yet with our computing resources, and it for very complex flow. Say you want to look at flow through an engine, right? Aerodynamic flow through an engine. That is something which has a lot of uncertainties. It's something that we look at a lot in aerospace, which is how does my air flowing through my engine look like? It has a lot of chaos in essence. So DNS for that type of flow situation is something that engineers would really like, but it is currently not possible. So we have to resort to a combination of RANs and LAS, and a bit in between. And so some specializations, like in this something called detached eddy simulation, etc. But those are used for, again, different flow problems. But on the surface, we mainly look at RANs and LAS. Yeah, and of course, we always require physical validation where it can be done. That is for a boundary layer wind tunnel. So I mean, when you want to simulate like flow through building, like for example, for flow across the Burj Khalifa, for example, that was simulated in a very using a wind tunnel, and it has to be so what we call is ABL wind tunnel. That's atmospheric boundary layer, because the entire atmosphere has a sort of boundary layer. Anyway, I will not go too much into that. I think I would need to get into numerical methods commonly used in CFD. Now, these are not there are a vast number of numerical methods that are used to solve partial differential equations in general, but to solve the equations of fluid dynamics and those that govern flow in a sense, like for example, a simple a convection or an advection, which is that fluid moving from one part to another, or diffusion, which is that um, the amplitude of something decreasing over time. These are really very simple flows, easy to model, but they're also part of computational fluid dynamics. So the numerical methods that we use to solve are mainly finite difference, finite volume, and finite element methods. Have any of you come across this before? Hello?
Yes, Shruti.
Yeah, yeah. Anyway, has anyone come across this before? The finite difference, finite volume, finite element methods?
Yes, yeah.
Yeah. All right. So anyway, the finite difference method basically means that you approximate your derivatives in space and time, or multidimensional space, by assuming by the field values at every point. So what you do is, when in CFD, which is that to solve the equations of flow dynamics, you need to solve for flow properties at different points, right? And you cannot do that without a certain matrix, because if you had to solve for all the points in a given surface, if you had to do that, it would be infinite number of points. So you discretize it, which means you split it up into several parts, and you solve for those properties at each of those points. And that kind of splitting is called a mesh. A mesh, in essence, it has several elements. So all of these methods, finite difference, finite volume, finite element, they use meshes, which is basically split up surfaces with made of these small elements. So each of these small squares that you see here is an element. And so finite difference, basically, yes, it you split your derivatives, as you can see, ui plus 1 minus 2 uij plus 2 ui minus 1, using the values at every single node, which is at the corner of each element. And then you derive a formula for that. And but the thing is, this can be sort of computationally intensive, and it's not very efficient when you increase the scale of your equation. So if you're going with a very complex set of equations from 1D to 2D, even that would make a large difference in the solution of this, and of using finite difference, and it would also be computationally expensive. Um, so generally, when you start out learning fluid dynamics and numerical methods, you start out with finite difference to get a feel for what the flow would be like. Now, another thing with finite difference is that when you refine the mesh, which is that when you reduce your delta x or delta y in each direction, that means your flow would become even more accurate, which is that you're introducing more points and more elements on which you solve your equations. So you get more detail, right? So that's what it means when you say your flow has become more accurate. Your solution is much more accurate. Finite volume is, yeah, so I think I would, yeah. So basically, finite volume is you look at your flow in terms of flow properties, which are averaged, which is that given this particular set of equations, I assume that my flow properties are um, constant across each cell, which is that, sorry, which which is around, I would assume that my flow properties are constant across each cell, which means there is no variation within a cell or an element. Yeah, when I say cell, I mean element as well. So there is no linear or there's no non-linear variation across each cell. You just take that each element has just one value, so to speak, for itself, right? And you solve in terms of elements. But in finite difference, you solve for nodal values. In finite volume, you solve for elemental values. And but finite volume is it's sort of a compromise between finite difference and finite element, because it does give certain accurate values and it does not take too much computational time like finite element. But the fact is, it does not give too much detail, and that can be a hindering aspect when it comes to different flow problems. So now finite element is, so this is a very interesting way of looking at it. So finite volume and finite element are what we call weak methods for solving partial differential equation. Finite difference is more of a strong method, which is that you arrive at your solution directly, which is that there is only one solution for a particular set of equations. That is what finite difference does, or and some other direct ways of solving differential equations. Finite volume and finite element are weak, which is that they kind of they reduce the constraints on the boundary conditions of your governing differential equations, and they make sure that you have probably a set of solutions to choose from. Now, which we can choose as the right solution depends on what is physically satisfying. And what we say in the world of numerical methods is that it should be entropy satisfying. It should not be entropy violating. Say, for example, if I get a solution from a finite element or finite volume method, which says that, my flow through around a sphere in 2D or 3D, ideally you'd imagine that it would go around the sphere and not through it. But if I'm getting a sort of a solution which says that it should go through the sphere, that is inherently entropy violating, which is not physically satisfying. So you would not take that as a solution. So what finite element and in finite volume, in the end, what it does is that the way that these equations are simplified for finite volume that I've shown here is a sort of direct way at arriving at it, but the real way is what is shown here with the finite element method, which is that in order to reduce the constraints on make my differential equations so difficult to solve, I reduce the constraints a bit and I introduce something which is called a weighting function, and I multiply it with the equation, which is that I'm saying that, okay, I hold a certain set of constraints, but I also relax them a little bit using that particular weighting function. So in finite element, you solve for your field variable, which is your u, and as well as your weighting function, which is your phi, which is given over there, 5ki. So what I mean is that given a particular mesh, right, I refer to, and this is a nodal solution, finite element. Finite volume is just sort of deconstruction of that, but finite element solves for the values at the nodes in the I, J, K dimensions. So phi ki refers to the weighting function value if at the kth node of the ith element, so to speak. So one thing with finite element is that you can get increasingly high order, a high order solution, which is that your solutions would become even more and more detailed as your order of solution increases, which is that I'm including more variables and increasing the space at which I make particular approximations. Um, so yeah, ideally you would expect that the accuracy increases. Are there any questions so far? Hello.
Sorry, ma'am, not it from my side.
Okay. Okay. Yeah. Anyway, so yeah, so finite element can be divided into two different types, which is continuous FEM and discontinuous FEM. So continuous FEM is that given a mesh that is given a surface, sort of solution surface over which I want to solve my equations. I assume that adjoining elements, that the interface of adjoining elements, uh, I don't have a I make sure that they're accounted for. That is at the nodes of each element. I make sure that I don't introduce any different discontinuities. I make sure that given a value a at the node one of element one, if that particular node is joined with node two of element two, I would I would I would make sure that I include whatever contribution there is from node two, physical contribution from node two to make sure that it is physically satisfying, that the node one value for velocity or pressure or whatever it is not out of balance because of it. So I treat each of the nodes of the elements as one while I'm making my solution. I hope that made sense. But in discontinuous FEM, and you can see the discontinuous nature over here of this thing. So each element has its own set of nodes and its solutions, which is that if I have a solution, if I have a value A for node one at element one, I will also have a separate B for node two of element two, if node one and element one, if they are joining, that is. I would treat them as essentially discontinuous. I mean, there is no, like any function, if you draw it across the elements, there is no continuity unless, I make some sort of approximation in plotting it. But that's what discontinuous FEM does. Now, continuous time is used mainly for structural and heat transfer problems because in different numerical methods are used for different types of differential equations. Like each differential equation has a character based on how it behaves in space and time. And so a couple of them, different types are hyperbolic, parabolic, and elliptic equations. And each of these have to be treated differently on how you numerically solve them. So continuous FEM is used mainly for structural and heat transfer problems. If you're trying to solve maybe the elasticity equation or Fourier's equation. Discontinuous FEM is used for, it's increasingly being used for fluid, plasma, and electrodynamic problems, which include flow of a non-solid substance, in this in the physical realm. Yeah. So that's what discontinuous does. I hope that was clear. So yeah, the need for higher order methods and HPC. HPC refers to high performance computing. Now, Higher order methods, as I said, you want to know, suppose if you're in academia and you want to know, suppose you're designing a pipe system, even as simple as a pipe system, or if you're a pipe engineer and you are you're curious enough to have the time to see that, okay, I'm not able to pass my fluid through my this thing. I'm experiencing certain delays over the water line. I cannot go to every single point and figure out the defects. So I want to see what I can do from a simulation perspective. So you want to know where, for example, clogging is taking place, or you want to know why it is happening, or the what is a factor, if rusting is a factor, or or the flow degradation is a factor, etc. There are a variety of factors that can cause certain engineering problems. So you would want higher resolution in certain parts of the flow. And that is essentially what I mean by this desired increase accuracy of the results. To, you would want more detail, right? The other thing is that you would want higher efficiency, that is lower computational time. This is, I think, easily understandable. If you have to use like 10 computers to solve a particular problem, it's not very efficient if you don't have the resources, or you don't have the funds or the access to such resources, and they could be used in a much better way. So you would want, that's why we would want high performance computing, which is that algorithms which scale easily, and that is something that BosonQ Psi is looking at as well. Quantum algorithms, which for different problems are much faster and much more efficient. Quantum computing, which digresses from classical computing in almost every notion of thinking there is. So that is one thing that they're looking at. Cost effectiveness, I think that is self-explanatory, and better scalability, which is parallelizability, which is that if I am given a particular problem in which can be, solved by, which is like in say one dimension, and I would want it to be solved for the same thing in 3 dimensions, or for a higher mesh, or a bigger mesh, or say I'm given the solution for a small car, and I would want to know what it looks like if it is in 3D, and if it is, say, 10 times its size. So I am sure that's a bit of a poor example, but I hope that makes sense. So you would want your solution to be scaled. To parallelizability is that there are different ways of writing algorithms, and serial algorithm is when it's written just by one computer. Parallelization is done by several computers. So better scalability. Yeah. So both of these are extremely important. Now, why DGFEM? So discontinuous Galerkin finite element method. There is a difference between discontinuous finite element method and discontinuous Galerkin finite element method. Galerkin was, I think he was a pioneer when it comes to variational methods and in mathematics. And this is probably the simplest way of looking at a particular problem, which is that when I mentioned earlier, which is that for a finite element problem, you solve for the field variable as well as a weighting function, right? You model these using certain, you can call them basis functions, right? Now, what Galerkin method does is that use the same functions of approximation for both the field variable as well as the weighting function. That's essentially what it means. And, it simplifies the equations, it simplifies your understanding a lot when you use the same functions for both, and it makes life a lot more fun. So that's what Galerkin did, and you would find that when you first start learning finite element method, Galerkin is the first way you get introduced to it. Yeah. So now, why you would want something that is discontinuous Galerkin? I mean, given problems which have discontinuities, that is, like say an aircraft traveling at near the speed of sound, you would definitely see a few shock waves everywhere, and those are discontinuities in the flow, which is rapid changes in flow properties, over which resolution is very, very difficult. So there for example a tsunami, for example, that rapidly spreads across a city, and over time you want it to behave a particular way, and it does not. That is, it has certain discontinuities, right? If there is a random shock that appears out of the middle of nowhere, you would want to know how to resolve that, and you cannot know this ahead of time. So just using like a lower order method would, like for example, if I'm using an averaging method, right, and I would say that okay, I know on an average that the flow goes, it goes from one location to another, but you would want to know how it goes that particular way. You cannot know that using a lower order method. And that's why you have discontinuous Galerkin, which is that when you're solving the equations, you solve for two values at the same interface, or two or three values, depending on how many connections there are or how many dimensions there are. So if six or seven elements are joined at a particular point, you would have six or seven separate values for um, uh, those field variables, right? For those nodes. Um, yeah, are there any questions so far?
Yeah, just one from on my side. So
Sure.
talking about the continuous and this continuous FEM. So if you just
Mm-hmm.
take this continuous solution and then you just suppress our nodal data points, does that make it a continuous solution, or like there's more to it?
In some essence, yes. I mean, on a very high level, yes. But your the number of variables that you solve for would definitely reduce, but you would also lose a lot of detail. That's basically continuous again. Yeah,
All
and
right,
the way you implement your boundary conditions would be very much different.
all right, all right. Okay.
Yeah,
Thank you.
yeah. Um, so Yeah, so coming back to DGFEM. So yeah, so to resolve discontinuities, to make sure that you don't have any surprises in the flow that you don't know of before, which is why one of the reasons you can use DGF, DGFEM. So another thing is that if you want to make a solution much more accurate, you want to know details of a particular flow, you can either try increasing the order of your solver, your numerical solver, or that you keep the same order of the solver, which is that you don't want to spend more money or you don't want to use a different algorithm. We just refine the mesh a little bit, which is that you increase the number of elements over which the equations are solved, right? That's a very simple way of doing it, and it's almost that's the most straightforward way. But both of these have an importance for an accurate solution if you want more detail. So using a very low order solution, say finite volume over like 10,000 elements, or in many cases, like people go up to like 100 million mesh cells, you're not going to get anywhere. So you would have the same resolution. You would not have more detail. Not necessarily would not have the details that you desire. That is. So increasing an order of approximation is very much important, especially if it is for a very critical problem. Yeah. Now, now HP adaptation is basically the numerical method term for increasing h, which reducing h, sorry, which is the parameter for mesh refinement, for mesh length, and the order of approximation, which is p. So p is the order of approximation for an accurate solution. And you would want, and what is seen with DG is that as you go higher, when you increase the order of the solver, your accuracy increases rapidly. The way, and I will show you that for a 1D problem later. But it's really quite fascinating the way that the way at which it increases across when you increase the order of a solution. And stable viscous discretization, that is basically saying that you know that you have discontinuities in a flow, but you don't want them to be too discontinuous. That is, you want to smooth it out and see how the particular shock or phenomenon happens. You want to know how it leads up to that, and that so that's why you use viscous discretization, right, to resolve that particular discontinuity. Yeah. And extension, this cannot be done in a lower order method, not as easily. Not, I mean, at least it would, you would achieve some sort of resolution, but it would not be as much as you could after increasing the order. An extension to variational space-time algorithms, that is essentially a fancy way of saying other finite element algorithms, right? Yeah. So this is in 1D, and I know this looks like a lot of math, but bear with me here. It's actually quite simple. So given your original equation, or imagine that you want to solve for a variable u, which is governed by, it varies in time when and it also varies in space using this particular f value, which is called a flux term in space. So this particular du by dt plus df by dx is equal to 0, and that's what you want to solve over a particular domain, and you're given certain boundary conditions, which is that, at, for example, at time equals 0, I think my solution looks like this across the space, or at this particular time I see maybe an external discontinuity, which is that something else is hitting it at that, only at that particular time. That's just different ways of interpreting boundary conditions. So as with finite element methods, you want to reduce the constraints on this, at least you want to make it look mathematically that you're reducing the constraints on this. So you multiply it with a weighting function, and you change the set of your equation, which is that, I have a term which, when you see the third equation right over here, that is, which is that, you have a term over the volume of the, so which is that, okay, so if you want to solve this particular equation over, say a sphere, right, a very large, perfectly innocent sphere over there, and now you have this, the first integral term that you see over here is solved over the main volume of the sphere itself, which is that the entire body of the sphere. The second, which this is more of a, this is also over the volume of the sphere, but since it includes a bit of a gradient term, we don't really interpret it that way. This is a volume term, but it's not as strict as the first volume term. And the first volume term is what is used for time stepping, which is that if we do not resolve this, you will not know properly how, or you do not, calculate it correctly, will not know accurately how the solution varies in time. This is more, the second term over here is more for spatial variation in the volume, right? And the third is where your adjoining cells affect each other, which is that if I have two elements joined with each other, which is often the case, 2 or 3 elements joined, I want to know how the values in the first element affect the second, or the values in the second affect the third, and so on. So that sort of coupling effect is what is seen over here. So this particular term is for the boundary variation, which is that the boundary of each element. So K here refers to the kth element. I here refers to the ith node. Now, so this is, I mean, imagine this in 1D. Suppose you have a domain from x equal to 0 to x equal to L, and you have, say, n elements, where you divide it up into n elements. So that means you would have n+1 nodes on the surface. But what you do is you approximate your equation using different orders, which is you approximate your solution using each order. So each of these values over here, each of these splits. So this split is one particular element, and this is in 1D, right? Now I have, these two are my physical nodes, but I try and approximate my solution using invisible sort of nodes in the middle when I increase the order, which is that, and that's where you have three. So from a physical point of view, these three would not exist, so to speak, because the main physical nodes are these two. But from a solution point of view, these three exist, which is that I'm using these three nodes for forming my solution. But when I look at it from a physical point of view, which is that, you know, you only solve for the value at two nodes, not for three. I hope that made sense. Um, Yeah, so that is for p equals 1, p equals 2, p equals 3. So these are basically these weighting functions. Yeah, so you approximate them using these smaller basis functions. Basis functions are also known as weighting functions over here. So the same way that you interpret the this is the particular weighting function is approximated in one way. You use the same Lagrangian basis for the this is okay. I need to come back to this, which is that weighting functions can be approximated a different way, which is that I'm just saying this can also look like different polynomials. Lagrangian basis is to some extent polynomial, but it can also look like trigonometric, for example, right? And you use the same, and the Galerkin formulation says that I use the same um, basis functions for my solution. So yeah, so you approximate your solution u, which is what you're solving for over here, as a combination of coefficients and basis function values, right? These are called basis coefficients over there. So which is that so what this means, this entire term is that for each element m, I I say that my solution is made up of of smaller this combination of values across different nodes. So suppose my order of solution is p, which is that I want my solution to be pth order accurate, which is that um, I want it to be only so much accurate, right? You're quantifying that with a number which is p, and I say, and that what this means is that there are p plus one nodes at least in 1D. It means that there are, if you want a solution of p accuracy, you would have to approximate it across p plus one nodes. For example, over here, which is that um, I want to find out my values for these two nodes, and I want it to be first order accurate, right? So I would have p plus one, which is two values for each node. So what it means that the value at each element is made of the unknown values of these two nodes. Whereas for this, when you again, this is to some extent related to mesh refinement, at least the visualization part of it, which is that in each element, I want it to be second order. If I want my solution to be second order accurate, I say that, okay, I want to approximate it using the values of 3 points. So that's why you take p equals 2 over here. So your solution over your entire domain is essentially the sum of um, approximations over p plus one nodes over elements. So over n elements, ne elements, right? So essentially what you're trying and what you solve for in the end is for these coefficients, which is u, m, j, right? Which is that the basis coefficient value at the jth node for the mth element. So this is what you're trying to solve for. So in unknowns, when you try to look at the number of unknowns, which is for each element, you're trying to find out the umj value. So you have p plus one unknowns for each element, and you have n elements, which is that n times p plus one unknowns. And this is again just in 1D. When you go to 2D and higher, depending on the way you construct your or the number of unknowns you want and your order of the solution, the number of unknowns will vary. So yeah, so a Lagrangian basis is especially very interesting because it's sort of easy to understand and it has local support, which means that each of these functions, their domain is constricted to this their own element, which is that phi mj has no effect whatsoever on, or does not have any presence on the m plus one element, because these basis functions are sort of focused on the mth element, and the m plus one or m minus one element, right? So they have what it's called local support, compact support, which is that suppose my first basis function has a dominant value, or like a value of say of one, and at node one it does not have that value at the second node, right? And you can see that if a particular the first, each basis function has a dominant value in its own node, right? So it is that sort of like a Dirac delta function, which is that it has not Dirac delta. This is more of a canonical delta, which is that it has a value only at the matching node. Are there any questions so far?
So, Shruti, I just want
Yeah.
to ask one thing, and I think so. Some people might have the same doubt. So, in the flux function that you have explained in the figure, um,
Mm-hmm.
that flux function, can you tell what are different type of techniques that is being that we use in DG methods?
Sure. I'm coming to that. That
Okay.
would come somewhere over here. You may talking of numerical flux functions, right?
Yeah, numerical flux.
Yeah, yeah. So I'm coming to that. Yeah. So yeah. So when you talk of in DG, the main approximation that you make is that you're not making any approximations. So this is just a different way of viewing the differential equation. The main approximation starts when you say that your solution is made up of smaller contributions across invisible nodes. So over here, like p plus one nodes within each element. So that is one approximation you do. And obviously, when you increase the number of Lagrange nodes and you increase the order of the solution, the number of these nodes increases, so you get much more detail across each element, how the solution varies. In finite volume, as I mentioned, I think several slides ago, each element has its own value. It does not vary across the element, whereas that is not the case in DG. Anyway, so yeah, I heard. So the Lagrangian basis is explained. Yeah, and now once I'm done approximating my solution like this, I kind of put it inside the each term. So this is the first very integral term, which is made up of so you try to solve the equation, the integral inside the equation, and this particular term is just you try and you substitute this formulation inside that, which is you're approximating the solution into this. And you try to make the equation in terms of the basis coefficients instead of the actual field values. It does not, we may not think that there is a difference, but there really is. But yeah, what you're solving for is these basis coefficients. So each term, each element has its own mkij, which is that the what it that is that each element has its own mass matrix over here, if you can see this. And the M1 refers to the mass matrix of element 1, element 2, and MNE, or it refers to the mass matrix of element N. What it means is that it refers to um, the physical contribution, the presence of each node. That is, if I have p plus one nodes within an element, each one has a separate contribution as a result of its existence, right? And that is why I have that mass matrix. And when the solution, when your equation marches through time, or your physical phenomenon goes through time, each node has a say on how it will march through time, or how its particular value will march through time. So that's a sort of reductive way of looking at it, but I hope that makes it easy to understand. But that is what your MKIJ means, which is that the mass matrix component for the ith um, basis function at the jth node, or the you can look at it either way. So yeah, and then that is the mass matrix contribution. And for each element, this is what is done. And then once you solve the entire equation as a whole, that is for n elements, you have a global mass matrix. So each of these smaller ones, mkij, is a contribution to a local mass matrix, which is mk, and then you assemble it all together, which is global mass matrix. Now, the other interesting way of approximation is using a numerical flux function over here, and that's yeah, that's a fancy way of um, trying to say how your flow properties move across discontinuities. So, as I mentioned earlier, this particular term is a boundary term, which is that it kind of tells you how elements interact with each other at their boundaries, right? And in order to characterize this, you have something which is called f hat, which is the numerical flux function. So what it says is that I say that my solution at the boundaries are a factor of the values at the left and the right at the boundary, and which is perfectly logical. I'm gonna okay, not, I don't have that particular picture over here, but given a particular interface, or this node, say, which is at the interface of the kth element and the k plus 1th element, I would obviously assume that whatever goes in or comes out of the interface at that particular node is a function of what happens at the last node of the kth element and the first node of the k plus 1th element, which is like the properties to the left and right of the node when you sort of look at it from a distance. But since these values are inherently discontinuous, you if your value at the k at the left, the last node of the fth element of the kth element is, say, 25, you would expect it to be, say, 27 or something else at the first node of the next element. So whatever goes in or comes out, I'm saying, using my flux function, what flows through it is is a function of the left and right values at that interface. Um, so the approximation that you make here using that is saying that you think you know how it would flow, or it's not very exact in saying that, okay, and it is what is best for the particular problem. Like, it would vary depending on the kind of solution that you desire and the kind of solution for that is perfect for that particular set of differential equation. For example, if you have a solution with many shocks, you would expect better results using something like a row flux, which is another fancy way of saying that it's more of a very elaborate way of accounting for the discontinuities on the left and right to try to model how this particular terms looks like when values of flow, when how the elements interact with each other. It's and Rowe, he's a professor. He's a professor at my university as well. He was the one who came up with this very ingenious flux function, which is that to model shocks and to make it simpler to model discontinuities, he modified this particular flux function, which makes it easier to see um, physical shocks across different elements. So different types of fluxes, numerical fluxes are there. You have the Gordonov flux, you have Rusnov flux, and Rho flux. You have the HLLE flux, which is that fancy ways of uh, basically modeling, trying to see what your solution would look like for a set of physical equations. Um, I hope that answered your question. Yeah.
Yeah,
Yeah.
thanks.
Yeah. So yeah, so once that is done, so what you do is you RKI refers to the residual, which is that the non time derivative part of my equation. So this entire part is what is called the residual. Um, so you try to solve that for a reason. So you have basis functions and you have basis gradients, which is that the changes across the while using modeling a solution across an element, you obviously you have some sort of weightage given to the values as well as how it changes across the element, right? That counts for the order as well. So as you increase the order, you would expect a finer resolution for the gradients, more details coming into it, the gradients. So this is a pretty important term. F refers to the analytical flux term, which is that modeling a set of equations this way, you say that du by dt plus df by dx. F is a function of u in some way. So when you're modeling, so what you do is with your set of equations, you're given an initial condition, which is that at time equals 0, you're given this set of values for the basis coefficients. And as you march through time, the values will change depending on how you march through time. And you sort of, it's like I'm assuming an initial value and converging to the actual solution. That's how equations are solved. Um, so yeah, so F refers to the analytical way of looking at this. So which is a mathematical function of the approximated solution, which is, I hope that makes sense. And then F hat refers to what comes in or comes out at each of these nodes, depending on the values of the left and right of each node. Yeah. This I'm talking about this in like 1D because it's much more easier to explain. And then you form the discretized equation, which is that you solve for your basis coefficients, which is like each of the n times p plus 1 values over here. So capital U refers to that. Small u refers to the field variable in itself. Capital U refers to the basis coefficients. And m plus r of a, which is the mass matrix, which changes through time, plus r of u, which is like the residual, which is a function of these um, basis coefficients equals 0, and that is your equation. So the mass matrix is it's like an n times p plus 1, n times p plus 1 square matrix. And this is again in 1D, right? R is a n times p plus 1 times 1. It's a huge vector. It's a huge vector where you have p plus 1 unknowns for each element. So what? Uh, yeah. So basically, what you do is you try and solve this. You try and form these terms for each element, and then you solve it as a whole, which is that given your loop, which is that you're marching through time, you have your initial condition. You want to see how your solution looks like at different times, right? So you inside your loop, you form your gigantic mass matrix by assembling these two, by assembling like the element mass matrix is over here. So you have this gigantic matrix over here, and you have this large vector of n times 3 plus 1 unknowns. And you you basically try and march this through time, which is that saying that okay, I have my solution at t equals t. I want to see how it looks like at t equals t plus 1, which is and you have different ways of doing that. So the simplest way of doing this is that du by dt equals minus m inverse times the residual, right? And yeah, and you're saying that my solution at t plus 1 is going to be a function of solution at t plus my du by dt term times delta t. So there are ways of modeling that as well. And the higher order you go, that is because you're going to you have more variables to solve. You also need to make sure that you have a stable time stepping method, which is that you increase the order in space. You also have to increase the order in time. Otherwise, you don't want a discontinuity there as well. I hope that made sense. Um, so yeah, so that's how there are different ways of time stepping, which is that I can just say that, and I wish I had a slide for that right now, but if it's a linear combination, which is that my delta u for the next time step, like ut plus 1 is ut plus delta u. Now, ways of modeling this delta u, I can say that it's either equal to du by dt times delta t, which is a linear way of looking at it, or various different ways of modeling that particular term. So, yeah, for the higher order terms, you would need higher order time stepping, which is that for finite volume, for example, which is basically p0. It looks at just one value for each element. Anyway, for that, I can use a simple time stepping, and it should be very stable, which is that I'm using a very simple order in space, I can use a very simple order in time. But as I go higher, I run the risk of my solution not converging, or it becoming unstable because my discretization in space and time are not compatible. Again, I hope that made sense. Um, yeah, so you have different ways of higher order time stepping, which is RK2, which is runs good at 2, which is I model my my delta U, that is UT plus 1 is UT plus delta U, in different ways. Using a two-step procedure, which is what RK2 is. RK4 is I split it up through different parts in time, so 4 different parts in time, and so it's a high resolution to time as well. And then various other methods are there, which are different. These are also specific to the types of equations that you're trying to solve. Are there any questions? Hello.
I think so. There are a few questions which we can take at the end of the session.
Sure. Okay.
People are standing in the chat.
Cool. Okay. Yeah, okay. And so this is an example for DG on 1D shallow water equations. So basically what the situation is that, you're given a domain like this, and the initial condition is, say, a giant wave like that. You want to see what your this is, imagine a pool of shallow water which just has the initial peak or a tsunami like that at t equals 0, and you want to see how that spreads through time, right? You have two balls over here, and you have a set of equations governing it, which is the shallow water equations, and you want to see how it looks at, for example, this is at t equals zero point 0.2 seconds, which is that what basically says is that once I have a giant peak like that, it will spread into two smaller peaks, and that is what my solution should look like at t equals zero point 0.2, and this is the exact solution. And this is on a mesh of about just 8 elements, to because it's easier to visualize the effect of increase in order on a with a reduced number of elements in the mesh. This has about 8 elements, and so this is my exact solution, which is what it should look like. And just at p equals 0, it's the solution looks like this, and you can see the discontinuities over here, which is that each element has its own you know um, sort of value over there. And this is expected of finite volume, right? Each element has its own, only one value to explain how it varies across each element. And you can see the discontinuities over there. This is at P0. And so, which means that if I had a finite volume solution using just 8 elements, I would not have a very pretty looking picture. And at p equals 1, it's slightly better. And you can see the difference between p equals 0 and p equals 1, which is that you can see this um, linear variation of the solution across the element. And you see these discontinuities over there. So that is it. And p equals 2 is a quadratic variation. You see it's more of um, a quadratic variation across each element, and each of these peaks over there are the discontinuities, right? So you can see the values, and then you can see slowly that it's getting closer to the exact solution as the order increases, and these discontinuities appear to smooth out, but that's really not the case. But yeah, they're slowly smoothing it out, and the reason, and at p5, after p2 you don't see much of a change. So which is another exciting thing, which is that beyond, say, p2 or p3, for most solutions you don't need to go much further, so you save your computational resources also that way. Because p3, p4, p5 look essentially the same, except for this particular sink that you see at p equals 5. But those are minor issues, really, and it depends on what you're looking for in a solution. So at p5, you see that it's very much closer to the exact solution. Now, the reason you may wonder why it's not exactly like that, is because this exact solution was modeled on a mesh of 64 elements, and this, you can say, is the exact solution on a mesh of 8 elements. So this is where the difference in mesh refinement also has a bit of an effect, you can say. Anyway, yeah, so that's it from my side. Let me know if you have any questions now.
Great presentation, Shruti. I think so. That was really insightful, very in depth into finite element and especially discontinuous Galerkin finite element. So we will start with questions. I will first go with the questions that were posted in the chat. So the first
Mhm,
question was by Nikhil Bagdam.
mhm.
He asks like if flow is not turbulent, it is linear. Suppose Reynolds number is 1800 for internal flow, then what is the use of CFD and equations? So, would you like to address that, Shruti?
Can you give me a bit of context? The Reynolds number is 1800 for what kind of flow?
For internal flow.
You mean inside a pipe?
Yeah, I think so. Internal, yeah, you
All
can say
right. So
fine.
he wants to know how to characterize that as maybe laminar or turbulent.
I think so. So, is Nikhil in the call? Maybe he can clarify some question because I didn't really understand completely.
Sure.
I think so. He left, maybe.
Right.
Um, I think
Yes.
is Nikhil here?
Yeah.
Um, Nikhil is not here. I think so.
Okay, I think he might. What he was wondering was if the flow, suppose because we know the Reynolds number for internal pipes, the critical Reynolds number is much above 1800. So if it is laminar flow, what is the need for CFD in that case?
Okay.
Um, Say you don't know the material of your pipe. I mean, you don't know certain inherent factors that affect because you know that your Reynolds number is 1800 for a particular flow situation, yes, but that only describes your inertial and viscous forces. There are a variety of other factors that may come into play, which is that pipe flow, for example, is affected by um, the not just the material of fluid and other things. It's also like the surface tension and pipe roughness. These things which or in discontinuities in your pipe surface as well. And you have a largely uneven pipe, not just a very normal flow. Suppose you have your pipe, you want to know what your pipe flow looks like. If you change your pipe shape a little bit. CFT makes it a lot easier to see how that would happen, whether if it remains laminar or it transitions to turbulence, because as you know, it takes very little for a flow to become turbulent. Very little. It's very easy for it because turbulence is nature, right? Laminar flow, in fact, is an outcast of nature, so to speak. So CFT makes that easier instead of solving your equations like by hand. Um, yeah, I think that's the answer I would give for that.
Yeah, yeah, I agree to that. So another question that is put by Shabir Hussain, he asks like, finite volume is implicitly conservative in nature, which is the foremost requirement for the fluid flow. Is
Mhm.
finite element is also implicit conservative in nature? If not, then how are we going to deal with it?
It is. It is. That's the reason it is applied for these equations. So there are, well, as I mentioned earlier, sort of it is. I mean, you may not see that, but it is the way that you imply it being conservative is that you would want it to be a TVD method. I think I understand that. Or you want it to be entropy satisfying, and for that, again, finite volume is it's a special case of finite element, right? And on a mathematical way, there are many mathematical point of view. There are many solutions that you could have. It just so happens that depends on the flux function that you use. Again, whether you do arrive at the right conservative solution.
Yeah. So just to add to that, and I think so that was a good apt answer. And to just add on to that, yes, finite volume will be conservative both in global and the local sense. Finite element is conservative in the global sense. In local sense, though it is not, we say that locally it's not conservative, but the formulation doesn't end there. We basically do the assembly process back to the global. So at the end, basically, yes, it does. Solve not solve, I would say, but fulfill the conservation requirements of the equations of the fluid flow. Um, so I would like to ask people from the audience if they have any questions that they would like to ask. If there's anything on the formulation side that was something that was not clear, something, please go ahead. Excuse me,
Yeah.
yes, sir. Is it practically possible to implement two different polynomial order approximation for two different elements and then couple it up in an assembly process for an assembly? For
Uh, I mean, possibly for a yes, definitely for like maybe if you're looking only at two elements, but when you're looking at a large scale, that becomes very computationally expensive. I don't. It would be. It's possible, but you know, it would have to be certain special elements, like for example at the boundary, and you would have to treat them differently. You can't just randomly assign an element and do that. You would have to construct a code specifically for that particular condition. Uh, and I mean, that's as far as I know.
thank you.
Hey Shruti, really nice talk. Thank you for that. I have one question. So in finite volume and as well as finite difference, we can the same equations after some transformation can be applied to many different types of grid, like curvilinear
Mhm.
grids, let's say.
Yeah.
Can same thing be applied for the finite element method?
Oh yeah. So I mean, that's the I should have mentioned that probably, but what is happening over here in essence? Let me just share my screen. Uh, yeah. So what is happening over? Yeah. One second. So what is happening over here is that you're mapping it to a domain, which is that your curvilinear grids. It's just that it's a okay. Let me just come to that first. So curvilinear grids are those that look different on when you look at it on the surface, right?
So
You
I
know.
was thinking.
Hello.
Yeah, I'm listening.
Yeah. So curvilinear grids essentially look very different on the surface, but when you want to numerically solve them, you would require some sort of mapping somewhere it's
Right, right,
easy to solve the equations, right? And that is what this C does, which is that you know, on the global scale. Suppose I'm here at say x k plus one, and this is x k plus two. Restrict to the element. This is c equals zero and c equals one. So that is a sort of local mapping that you do here. And if you had any curve within your grids, or if you had any a differently shaped grid, that shape would come into effect as well. Or for example, if it was a non 2D or 3D element, you which was differently shaped, you would have or see maybe the area of the element come into play, or if you have different lengths for the element, the length would come into play. Like for example, when you're modeling this in 1D, your delta x would come into play. The Jacobian of the element is a
right.
very important thing. So um, that is accounted for in finite element, and by extension finite volume as well,
Right, right.
because finite volume is like finite element. So yeah.
Okay, so for that, if I understand it correctly, first you would need to perform some kind of grid mapping from whatever
Yes.
coordinate system into, let's say, a simple rectilinear, and then solve all your equations there.
Yeah. Yeah.
Okay,
Yeah.
all right, thank you.
So any other questions from the audience? So, if not, then
Questions?
I think
I'm
so.
just trying.
There's no more questions. Is there any question? Again, everyone? Okay. If not, then, so I would like to thank, on behalf of BosonQ Psi, to Shruti, for giving this such an amazing presentation. I know it's a difficult uh, challenge and difficult and challenging topic to give a presentation on, and as well as from an understanding point of view. But I think so you dimmed down really well, and I hope it was really insightful for people who are interested in this method. Um, it is definitely one of the interest areas for BosonQ Psi CFD team to look into this, and that is the reason we had one of the experts speak about this topic. And I would like to thank Shruti again for the amazing presentation. So just one announcement to everyone present here in the audience that um, this kind of lecture series will be continued by BosonQ Psi on other topics as well. And there is another great event that is that we are conducting, which will be announced in some time through LinkedIn or Twitter. But it basically will be kind of a lecture series for 1 month on different types of multiphysics simulations, and then we will have again experts coming in to basically give a talk on those topics, and then it will be followed by a hackathon, um, because boson QSI is in that intersection of multiphysics simulations and quantum computing. So you will hear about. Just be aware. Just letting you know, and be in the lookout of the emails and LinkedIn and Twitter posts on those events. We will soon release, and since you guys also like we have included you guys as in the subscribers list, so hopefully we will be able to give some information, and we won't bombard your email with marketing emails and all those things. But yes, thank you again everyone to join joining here.
Excuse
Um,
me. Just one more question, please.
sure, go ahead.
Sir, for the non-overlapping grid, is it possible to actually apply DGFA? Because is it possible to counter with the flux function because the grids are not overlapping for the non-overlapping grids?
Could you repeat that? I didn't quite understand. You have not.
For the overlapping grids, we can play with the flux functions. If the grid is non-overlapping, how can we account for the flux functions, numerical flux functions?
Uh, I'm not quite sure. I imagine that you would have to solve each part differently, each grid sort of differently, um, and maybe it would change your boundary conditions a little bit, as I understand. Yeah, depending on what each part is going to encounter. Yeah.
Thank you again, Shabi, for that question. As I was saying, I just want to ask again if anyone has any questions before I wrap up. Um, okay, so great. Again, on behalf of Boson Fisai, I would like to thank Shruti for this amazing talk. And I would also like to thank everyone in the audience for taking time and joining in and showing interest in this area. And definitely have a good night, stay safe, and stay healthy. Thank you so much, everyone.
Yeah. Thank you.
Thank you, Shruti.